In this video I will be explaining the probability distribution function with the help of example. In the last video we have seen a definition of probability density function. Okay, let us have a brief of that, and after brief introduction of probability distribution function, we'll take one example so that everything related to probability density function and distribution function both will be clear through this example. Okay, so in the last video I gave the definition of probability distribution function. The probability distribution function denoted by capital F, then this X indicates the probability distribution function of random variable capital X taking value less than equal to small x. So probability that random variable capital X is taking value less than equal to small x. So this is the definition of probability distribution function. This, when I write here equal and triangle, it means it is defined as. So probability distribution function of random variable x, it is denoted by capital Fx x, where suffix x indicate the random variable for which that distribution function is defined, and probability that random variable x is taking value less than equal to small x. Okay, so here less than equal to small x, if x is positive, so we can say that it is from minus infinity to that x. Even if x is something negative, that in that case also we can say that it is minus infinity to value of x. Okay, suppose if that small x is infinity, in that case there is no event, random variable taking value less than minus infinity or equal to minus infinity, there is no event doesn't exist. If event doesn't exist, the probability of impossible event or event which is not existing is 0. So that is why if I write Fx minus infinity, definition of probability distribution function, here small x is taking value minus infinity, so probability that random variable capital X is taking value less than equal to minus infinity. This is impossible event. Impossible event, right? There is random variable is not going to take value less than or equal to minus infinity. So this event doesn't exist. So event which is not existing, then that probability of that event is 0. So Fx of minus infinity is 0. So when I say Fx of x, it means it is from minus infinity to x, this entire segment minus infinity. When I say x is Fx x, this x means it is like this, it is from minus infinity to x. So probability of random variable taking value less than equal to small x, so it is from minus infinity to that value. So that is the meaning of Fx x. So Fx of x. Now if I write Fx of infinity, so probability that random variable x is taking value less than equal to infinity, in this case we know that your entire sample space is coming into picture, and random variable taking value less than equal to infinity, it means that since it is a cumulative distribution function, it is addition of probabilities, okay, up to addition of probabilities of all outcomes. So here it is going to be 1. So probability distribution function value is going to be 1. Probability distribution function is called it also called this one cumulative distribution function. So what it is doing, it is adding the probabilities of different outcomes which experiment is taking. If we are having all outcomes, right, x is less than infinity, it means all outcomes we have to consider, they will naturally come into picture. The probability of individual outcomes, if I am taking and adding all these probabilities, result is going to be 1. So that is fx of infinity. So answer is 1. Suppose I am having segment, random variable is taking value from x0 to x1. Random variable x is taking value between x0 to x1. So in this case, how to write distribution function? How to write distribution function for this segment? So what we can write here is, see, I will take a segment from infinity to x1. I will take one segment from infinity to x1. I will take another minus infinity to x1 and another segment from minus infinity to x0. So if I find the distribution function of this, minus if I find subtract or find and subtract the distribution function of this, then I will be getting distribution function of random variable taking the values between x0 to x1. Random variable taking value between x0 to x1 can be obtained by taking the probability distribution function for random variable taking value less than equal to small x1 and subtracting the probability distribution value of probability distribution function for the range minus infinity to x0. So for this I can write fx, I can write here fx of x2, and for this I can write fx of x1. So total fx of distribution function of this range minus distribution function of this x1 and this is x0. So this is the distribution function value, right? So that is the value of distribution function that x0 is x is less than x1. So if I write like this clearly, if I write it clearly, what I am finding here is probability that random variable capital X is taking values between this range. So definitely it will be fx of x2 x1 minus fx of x0. So whenever it is asked what is the probability that random variable is taking value between x0 to x1 in terms of its distribution function, so we can write like this. So probability distribution function, if there is a segment, if there is a random variable, it is taking value between x0 to x1. In that case you can find probability that random variable is taking value greater than equal to x0 and less than equal to x1, which is equal to distribution function of random variable up to x1 evaluated at x1 minus distribution function of random variable evaluated at x0. So this way we can write distribution function of a probability distribution function for a segment. If suppose if I am having distribution function, we can find density function. So we know that differentiation of distribution function fx of x dx is nothing but, so rather it is good to write to this side fx of x density function. Density, this is density function, probability density function. density function. This function gives the probability at individual values for individual values of random variable. So if you differentiation, so you are having staircase like diagram for the probability distribution function, and if you just differentiate that, you will find only peaks at particular values of random variable. So in that case, we are getting probability of taking value by the random variable at that particular instant when we say that it is discrete random variable. So continuous random variable, you are having different kind of distribution function graph. Their differentiation will lead to different kind of shape. So what from different density function we will get the individual probability, and from distribution function we get the cumulative addition of all probabilities up to that particular event. So since I am having small fx of x, which is differentiation of distribution function, so naturally density function can be used to write the distribution function. So it is fx of x. So when we know density function and you want to find distribution function, so it is just reverse operation, because density function of random variable capital X is defined as derivative of distribution function with respect to x. So exactly reverse operation when you want to find distribution function, so result will be like this. If I say fx of x2, distribution function evaluated at point x2, so it will be like this dx. And if I say distribution function evaluated at x1 minus infinity to x1 fx x dx, if you subtract these two things, fx of x2, let us assume that your x2 is greater than x1, then we'll be finding the probability that it is taking values between x1 to x2 in terms of its density function. I am writing the same equation which we have seen earlier in the form of distribution function. So fx of x2, fx of x1, right, this segment minus infinity to x2 and minus infinity to x1. So if I take distribution function of this segment, subtract it, so we get the probability for the duration x1 to x2. So same thing I can write in terms of f of x2, means it is minus infinity to x2, fx of x dx. This is for first one, and for second again integration minus infinity to x1 fx of x dx. Mind well, if random variable is continuous, in that case we use density function, that is fx small fx x. If it is discrete random variable, so naturally your distribution function density function is available in terms of probabilities p1 p2 p3 and so on. Here if I see that integration minus infinity to x2, one integration, and second is minus infinity to x1, so we can write this as x1 to x2 fx x dx, and which is therefore we know that this is nothing but probability that random variable is taking value greater than x1, greater than equal to x1 and less than equal to x2. Mind well, when random variable x is continuous, this equal sign, if it is there or not there, there is no issue. Here also there is no issue, since the integration of single point is always 0. When random variable is continuous, in that case this equality, even if this equality is not there, it is carrying the same meaning. So this is also the formula which is required many times. So let us write that clearly. Fx of x2 and minus fx of x1, so it is equal to the probability that x1 is less than capital X and capital X is less than x2, and which is nothing but minus plus x1 to x2 fx of x dx. So we can write this difference of distribution function in terms of density function. So like distribution function, density function also satisfies some property. Fx of x is always greater than equal to 0. Density function is always positive. It is always positive, and if it is not positive, it means it is 0. It is not taking negative values. This is one property. And another property of distribution function, density function is when it is integrated, the area under the function fxx is always 1. So density function integrated over its interval gives 1. So it is called valid density function. Density function is valid if its area is 1. Density function is valid if it takes values greater than equal to 0. These are the two properties density function must satisfy. In case of discrete random variable, we should put similar condition on probabilities. All pi's must be greater than equal to 0, and addition of all probabilities must be equal to 1. So that is the requirement when random variable is discrete. In case of discrete random variable, instead of probability density function, we talk about its probabilities of random variables. So all the probabilities, they are greater than 0, and summation of all probabilities equal to 1. So these are the two conditions when x is discrete random variable. X is discrete random variable. So there are two conditions here also. All probabilities must be greater than equal to 0, and addition of probabilities should be 1. So this is what we have to remember when we talk about the discrete random variable. So we have to use probabilities, and in case of continuous random variable, we have to use fxx. So we have defined discrete random variable is discrete. What is the probability? What is the mean of the random variable? When random variable is discrete, it is the xi, these are the values taken by the random variable, into probability that random variable x is taking value xi. This is the definition of mean. Right? Random variable is random variable. We know that random variable is a mapping from sample space to real line. Though name is random variable, it is not random. But arguments which are there to mapping the arguments, or we can say outcomes, those outcomes of the experiments, they are random in nature. So naturally, what value random variable is going to take, it is decided by what outcome experiment is going to give. So whatever outcome comes, it assign the values to the outcome according to predefined formula, according to predefined function. Random variable can also be called as function. It assigns real values to the outcome of experiment. So this is this we have seen when random variable is discrete, right? Discrete random variable. If it is a continuous random variable, the definition of expected value of x becomes, it is also denoted by mu x, where x is a continuous random variable. So it is x into fx of x. Random variable is continuous. It is taking the values, all values in the specified duration. So when duration is not specified, in general it is minus infinity to plus infinity. In this case it is taking all values, all real values between minus infinity to plus infinity, and multiplied by probability that it is taking that value. Suppose x is x1, so that time distribution function fx x1. So x1 can be, let us say, 0.001 multiplied by fx of 0.001, probability of taking that value, and addition of all these multiplications. That integration is nothing but addition. So addition of all these probabilities giving you the mean value of the random variable. So average behavior of random variable is given by mean. Is given by mean. Mean gives the overall behavior of the random variable. On an average, how random variable is behaving. On an average, how random variable is behaving. What way it is behaving. Average behavior. If you want to find for any random variable, you can use expected value of x. You can use mean. So this mean is a first order statistics. It is first order statistics of the random variable. So random variable x is random. So to characterize that, we have to characterize that we are having statistics, that is mean, variance, distribution function, density functions. These are the higher order moments, higher order statistics. They are there to characterize the random variable. And here I would like to tell you that random variable and random process, the difference is random process is collection of random variable. Collection of index sequence of random variable is a random process. The random process is having collection of random variables. So each random variable can have different mean, each random variable can have different variance, each random variable can have different distribution and density functions and other higher order statistics. So after knowing this mean, I will go to variance, which is second order statistics of random variable x. Variance it is deviation about mean. Deviation about mean. Random variable, how it is deviating about its mean value, or it is a measure of dispersion about the mean. It is measure of dispersion about the mean. Variance. So variance is denoted by rho x square, and it is defined as expected value of x minus mu x whole square. This E operates only on random quantities. Whenever there is a random process or random variable, E is used for making it deterministic. Expected value of random variable we know called as mean. Expected value of x square, that is square of the random variable, is called mean square value. It is mean of the square value. That is why it is called mean square value. Expected value of random variable is mean. Expected value of x square, that is mean square value. So here in this case, if you expand this, so you will get x square, which is purely random term. Mu x is deterministic. it is deterministic, we know its value, so expectation operator will not do anything with deterministic value. And here mu x square, here it is also deterministic value, expectation of deterministic quantity is the deterministic quantity. So here you can write expected value of x square, it is totally random. Here minus 2 mu x is a deterministic factor, so expected value of x, and again expected value of mu x square is mu x square, because mu x is a mean which is known to us. So here this expected value of x and mu x, so we get expected value of x square minus 2 times mu x square. This is mu x, this is mu x plus mu x square. So what we get is, what we get here is variance can also be written as expected value of x square minus mean square. So this is the formula which you can use, or you can use this formula. Okay, so variance, it is a measure of deviation about the mean, how random variable is varying about its mean. Suppose in this first graph I am plotting this is my mean. Okay, this is my, let us say, density function of random variable, and this random variable, see, random variable probability that random variable taking value equal to mu x is maximum, it is maximum, and deviation about this deviation, let us this variance if I take square root of that, okay, square root of variance, that is called standard deviation. So sigma x, and this is minus sigma x, so this mu x plus sigma x, and this one mu x minus sigma x. So deviation about the mean, deviation, this is deviation from the mean, it's plus sigma x, this is deviation from the mean minus sigma x. So if deviation is less, we can say that random variable is taking values near to its mean, and if deviation is more in this density function plot, you just see how this deviation is. The deviation is naturally here, deviation is more, so random variable is taking values which are away from the means also. Near to mean also there are some values, and values, since it is spread, so it is taking almost all values, it is taking almost all values. See here it is non-zero, so this is the probability that mu x random variable is taking value x equal to mu x is maximum, then probability is getting decreased, and here also probability is getting decreased. As we are going away from the mean, the probability is getting decreased. So taking the values near to mean, here also the probability is there, but here the values are distributed, right? Let us consider the class of 100 students, and exam is conducted for 25 marks, and mean of the class is obtained, average of the class is obtained. Let us say average of the class is 15. So if almost all students, they are getting the marks near from 13 to, let us say, 17, so what we can say that almost all students, they are near to average value, average of the class. So that it means that there is less variation, deviation about the mean is less. If suppose students are taking marks from 0 to 25, so all marks are covered, so in that case your variance is more. So variance is more, so it is taking more number of values, and variance is less, the random variable is taking values close to its mean. So behavior of the random variable we can test from its variance also. Variance is, it is a second order statistics, mean is first order statistics. If this mean and variance, they are not sufficient, then we have to go for higher order statistics. So then higher order statistics means moments, rth moment. So we can go r equal to 3, r equal to 4. So all different moments are there, central moments. All these moments we can use to classify that random variable from the other random variable. Now let us see one example to find out all these mean, variance and density function and distribution function of random variable x. Let us say that we are having experiment on die throwing experiment. In die throwing experiment, what is our sample space? Our sample space is f1, f2, f3 and f6. There are 6 outcomes. When die is thrown, we get one face at the top. So if die is fair, then what is the probability of occurrence of each face? 1/6. So probability of occurrence of each face is same, 5, 6. Probability of occurrence of each face is same since die is fair. So now we have the sample space. Using this sample space, it is beyond a point we cannot interpret this experiment. So we want to interpret this experiment. For interpretation of experiment, it is possible if we assign real values to each of this outcome. So let us use the concept of random variable, which I already explained in my earlier videos. So we know that random variable, if x is a random variable, so it is a mapping from sample space to real line. So f1 is going to x of f1, f2 is going to x of f2, where x of f1, x of f2, they are the real values, and f6 is going to x of f6, all they are real values. Let us say 10, 20, likewise 60. So my mapping is like this: x of fi is equal to 10 into I. So I is varying from 1 to 3, 4, 5 and 6. Here meaning hereby is, if face f1 is coming, then random variable is taking value 10. When face f3 is coming, it is taking value 30. If face f6 is coming, it is taking value 60. The values taken by the random variables, they are between 10 to 60. It is taking value 10 when f1 is coming, occurrence of f1. Die is thrown, and if you are getting f2, so random variable converting that f2 to real value, which is 20. So x, let us define, I am defining random variable can be defined in various ways. That values can be assigned using random variable. Mapping can be of infinite ways, right? Various ways we can map the outcomes